Welcome back everyone, Patrick here, and moving on to the next example. What we got to do is take each of these products here, we have to illustrate them with a diagram, and then we have to verify the product algebraically. So in this particular case, what I'm actually going to do is I'm first going to do it algebraically, then I'll show you how you can represent these with a diagram. So notice these are just binomials because there are two terms that are adding inside the bracket that are squared. They're squared binomials. So algebraically, what we can do is we can take this, we can rewrite it as x plus 3 times x plus 3, like that. And then you can just FOIL it out. So we'll do x times x, which gives us x squared. Then we'll do x times 3, which gives us 3x. 3 times x gives us 3x. And then 3 times 3, which gives us 9. And then notice those two, they're like terms. So we'd have x squared plus 6x plus 9, like that. So that's what this product ends up being when you expand it and then you simplify it. Now with a diagram, what we can do is, because notice how it's like x plus 3 times x plus 3, it's the same term that's being multiplied by itself. We can represent that as a length times a width. So it would basically be a square. So let's start off with the base, the length. So it would be x plus 3. So all you have to do is you got to create two shapes like this, two lines like this that represent both of these terms. So this can be like the x, and then this over here can be like the 3. Now this is different than, just want to mention this, than algebraic tiles, because with algebraic tiles, what it was, if we had like x, for example, it'd be a long line, then if we had like a 1, it would be a small line, like that. Here it's a little bit different because notice we're given different kinds of terms. So here we're given the x and the 3, but notice here we're given x and y. And over here we're given mx and n. So it doesn't matter what length here you're using, as long as you're just labeling both of them, whatever the terms should be. Okay, so just want to give a heads up that these diagrams that I'm making, they're different than algebraic tiles that I've done in previous videos. The process is the same, it's just these references are different. You can make the references whatever you want. You can make the x be a long piece and then the 3 can be a small piece, or you can make both of them be the same length. These are about the same length. You can make the x be small and then you could let the 3 be a large piece, like that. It doesn't matter, because once we actually create the rectangles within, we're just going to be multiplying the side. So you know what, I'll do this diagram, but then I'll show you a different way. I'll maybe show you how we could do it like this, or with a different length for x and 3, and how it doesn't matter. So over here we got x and 3, and then what we got to do is we got to create something like this where we got x and 3, like that. And then like we did with algebraic tiles, what we do is we create a large rectangle like that, and then any spaces here we create a horizontal line. Any spaces here on the base, we create vertical lines, like that. And so from here, what we want to do is we want to label a little bit more. So if this is x here, that means this is x. That means this is x right here. If this is 3, then this is 3. This is 3 up here. Notice this is 3. That means that this is 3. This is 3. This is x. That means this is x. That means that's x as well, like that. And now what we can do is we can find the area of each of these rectangles here. So this one would be x times x, which would give us x squared. This one would be x times 3, which would give us 3x. This one would be 3 times 3, which would give us 9. 3 times x, which would give us 3x. All right, and maybe let's, so we don't get confused with all these numbers, let's circle the areas over here so we could differentiate them from the sides. And so now all you have to do is basically add all of these up, and when you add them up, what do you get? Well, you end up getting this exact sum over here, x squared plus 3x plus 3x plus 9, x squared plus 3x plus 3x plus 9. And so that's going to simplify to that, right? So that's how you can do it visually. And again, these lengths here, they don't matter. So like if we did this same one and we just did, let's say we made x very small and then we made 3 very large, right? Again, you don't have to, but let's say we did that. So then we have x, and then let's keep 3. That's about the same size. And then we create the same thing. Again, it doesn't matter because we're still multiplying here, x times x, x squared. 3, this is x here, right? So that's going to be 3x. This here is 3. This here is 3. 3 times 3, that's going to give us 9. 3 times x, that's going to give us 3x. So we're still going to get those same products, those same areas for whichever rectangles are created. And again, the rectangles, the size doesn't really matter as long as you're labeling the sides correctly with whatever product you're using. Okay, so that's how you could do it with a diagram. That's how you could show the product with a diagram. And basically all of these are going to be the same because it's the same kind of format, even though the terms are changing, right? This, it's still a binomial here. It's still a binomial. So let's actually I'm just going to erase this over here, give myself some room. So let's do part B. So we got x plus y times x plus y. That's going to be x plus y, x plus y. So x times x gives us x squared. X times y gives us xy. Y times x, same as xy, put in alphabetical order so you can notice the like terms easier. And then y times y gives us y squared. These are like terms. So we end up with x squared plus 2xy plus y squared. So that ends up being the product. And then if we show this with a diagram, let's label this x, let's label this y. We'll label this x, we'll label this y. And then same thing. We just create, you could actually just keep the same diagram, and maybe that's what I'll do. I'll just keep this same diagram for reference and just change these side values. Right, so this would end up being x over here. This would be x. This would be y. This would be y as well. This would be y. This would be x. This would be x, like that. So let's go through each of these 4 rectangles. X times x, x squared. X times y, xy. Y times y gives us y squared. And then x times y gives us xy. When we add all of them up, notice we'd end up with that same sum. And then simplifying these 2 like terms, that would give us that 2xy over here. All right, so that's x plus y to the power 2. And then over here, we'll have mx plus n squared, which is like mx plus n times mx plus n. Now just be careful here because we got, it's still a binomial, it's still 2 terms, but this term here has 2 parts to it. So we'll have mx times mx, which gives us m squared x squared, like that, right? mx times mx, m times m is m squared, x times x is x squared. Then we'll have mx times n, which in alphabetical order, no, it would be m and x, like that. And then we'll have n times mx, which is the same as this, alphabetical order. Let's have it like that. And then we'll have n times n, which would give us n squared. These 2 are like terms. There's like a 1 in front of each of these. So we'll have m squared x squared plus 2mnx plus n squared, like that. So that's what the final product ends up being. And then to show this with a diagram, we'll let this be mx, we'll let this be n, we'll let this be mx. You know what? Let's make it really obvious. So let's maybe make these a little bit smaller. So we'll let this be n. And so we'll have a smaller length representing n like that. So then when you make your diagram, it's just easier to see when you're dealing with the smaller sides, it's going to be n. And then when you're dealing with the longer sides, it's going to be the mx. So over here, two long sides, mx times mx, m squared x squared. Here we got a longer side, which we obviously know is mx, and then times n, which would give us m and x like that. Here we got two small sides multiplying by each other, so n times n, that would give us n squared. And then we got a long side and then a short side. So that's like mx times n, which gives us m and x. Like that. So now to come to think about it, it might be better to use a long side and then a smaller side. So then you could obviously see which of these is multiplying. We know mx is going to be all the long sides and n is going to be all the short sides. So visually that might be a little bit better, representing a long side and short side for each of these terms. But again, it doesn't really matter as long as you're labeling all of the sides for all the rectangles correctly. But yeah, this might be easier to do. So either way, notice how when we add all of these up, we end up getting that same sum at this step, but then these two, they're like terms. So we can combine those, and that ends up being the final